So I made up a DE. I think it's a separable DE. It's got an initial condition. To solve this DE, we've got our work cut out for us, I think. I think you got to separate and integrate. Right, you guys? There's a kind of a key idea here. First of all, though, I'm writing this as dy dx. It helps me a lot. A y prime written as a dy dx helps me when I'm trying to separate and integrate. What about over on this side? You see anything you want to do? There's one key idea. I mean,
factor out the y.
Yeah, you need that. Sometimes students don't ever see that, and then this thing doesn't separate too well. So it's not a difficult algebraic idea. Please factor out the y, but you kind of need it. Once you factor out that y, then you sort of see how easy it is to separate, right? I mean, without that factored out, you can't. Adding and subtracting things doesn't usually help get things separated. It's usually dividing and multiplying that get things separated. So we're trying to separate the variables, and now I think I can do that. So that was nice. That factoring move was a key little move there. Yeah, I think I'll divide by y. I'll end up with a dy over y. I think I'll multiply by dx. I'll end up with 4x minus 3 dx. There's one more thing I didn't do here. What did I do?
Where did the 2 go?
Yeah, or the 2x, right? I didn't do anything with this 2x yet. I think I'll divide by 2x. The truth is, I could leave the 2 here and just divide by the x, but
We're going y by itself. Right.
well, maybe I don't want the 2 up there. Right, you're right. Let's divide by 2x. Yeah, I mean, I could do it either way, but let's do it like this. Cool. I divided by the 2x. Divided by the y, I got the dx over there. Yeah, I did it. We did the algebra necessary to separate variables, right? Now, we integrate. We integrate this side with respect to y, we integrate this side. Hey, this is classic again. We get this classic natural log of y. You know, technically it does have absolute value, but I'll probably lose those in a minute. Over here, I need to integrate that. Any suggestions? How do I integrate that?
You separate the fractions.
You have to use u, v.
Ooh, no, yeah, I don't need all that u and v stuff. No, I don't. You know, when you're dividing by one term, you can separate this. You can separate this. So it's a 4x over a 2x. What's a 4x over a 2x? 2.
Yes.
Minus 3 halves.
3 over 2x.
Or 3 over 2x. Right. Okay. Right. A 4x over a 2x and then a 3 over a 2x. And that separates into that. And now I think I can integrate that. This is the natural log of y. Let's see. Can you integrate a 2? Anybody integrate a 2?
2x.
Good job. All right. Thank you. And I like to think of that as a 3 halves. I'll pull the 3 halves out. And then I'm integrating a 1 over x. So what's that? ln of x. Anything else?
Plus c.
Thank you. Plus c is important in differential equations. We need the plus c, as you've seen, I guess. You need the plus c. Hey, you know what? I solved the DE. I mean, you got a solution to the DE. It is not explicit. It is implicit. It doesn't take much to make it explicit. All you need to do is solve for y, which means E both sides. So you're right. I mean, we're almost done. You know, you could stop right here and try to find that C. You can stop right now and try to find C. You do have an initial condition. Or you can wait and find the later C that you'll end up with later.
So solve for y and then just put the value in of y when y or x is 1.
Well, here's what I'm saying. Right. Right now, if I felt like it, y is a 3 and x is a 1, and I could plug that in. Y is 3, x is a 1, and I could solve for c right now. Then I would plug that back in, and then I'd still want to solve for y. I'd still want to e both sides to solve for y eventually. Anyway, I'm not really saying that's good advice. Let's go find this c right now. I think my advice is actually, let's find the C later. Let's E both sides, like y'all said. Y'all said E this side and E this side, okay? E, the log of natural y, just turns into y. And on the other side, I've got E to that long mess. It's E to all that.
But it simplifies out really quickly.
It does simplify. If you play that game, I tried to teach you, this is an important little game. It's E to the 2x multiplied by E to the negative 3/2 log x multiplied by E to the C. Now, even though I'm teaching you this and I'm explaining it to you, on test day or quiz day, some students will still put plus signs in here. So try not to do that. Try to understand what's going on, right? You E the entire side. The exponents are added and subtracted, but that means that the bases are multiplied. These multiplied bases lead you back to those added and subtracted exponents. And this simplifies big time. I'm going to call that C. I'm going to write it out front. I guess I'll call that E to the 2x, but this simplifies a lot. I mean, using our properties of logs, you can do something with this.
X to the negative 3.
You can move this power up here. That's a property of logs. You can call this x to the negative 3/2. I think I will lose my absolute value now. X to the negative 3/2. Oh, and then the E and the log cancel each other out, and you're left with x to the negative 3/2. Wow, dude, this is a beautiful, cleaned up, general solution. Explicit general solution. Beautiful and cleaned up. But because we have an initial condition, I won't stop here. I'll plug in that initial condition and try to find C. Plug in that initial condition. Like I said, it's y is a 3. C, I don't know. E to the x is a 1. So this is E squared. And then x is a 1. That's not bad. You know what 1 to the negative 3/2 is?
It's a tough one.
It's a tough one. You know what it is? It's the square root of 1. What's the square root of 1?
1.
To the 3rd power
1.
in the denominator.
1.
Good. It's a 1. So 3 equals C E squared. So what's E? I mean, what's C? 3 over E squared, or you could call that 3e to the negative 2. Some students like to decimalize it. I kind of like my pure mathematical answer. I don't really need to decimalize this. This is what C is. And if that's what C is, I'm prepared to write my final answer. Okay, here it is. My final answer, it's right here, except it has that C filled in there. I'm going to write 3 over E squared, E to the 2x, times this x to the negative 3/2. I guess I could move him into the denominator. There's a lot of different looks this could have, you guys. It could have E to the, you know what you can do? You can combine these E's. What would you do to combine these E's? Subtract exponents, and you would have 2x minus 2. I can move him into the denominator. He becomes x to the 3/2 in the denominator. I don't know. That's fine. To tell you the truth, this is fine. When it comes down to little nitty-gritty algebra, I'm not that picky. I mean, we're solving DEs, and we should be happy we solved the damn DE. And not too picky about the way this answer looks. But I do like these moves. I prefer you go from this step to this step and get these multiplied E's. It does simplify it quite a bit, especially with this kind of step here. All right, so that was a little more advanced. We did some easier ones earlier. Now we just got a little more advanced with that problem. I don't know. To me, there's a lot of little stuff in there. The key was at the beginning, though, to get it separated. That factoring move sort of helped to get it separated. All right, so I think you should do some 2-2 homework and try solving DEs, separate and integrate. But I'm backing up now. I'm backing up into 1.1, and we're going back into preliminary theory. And you have to try to keep in mind that you don't know how to solve any DEs yet. Now, pretend you don't when you're back in 1.1. You know, one of the things we do is we try to categorize these we talk about, you know, what this course is about. So differential equations, they can be categorized into two main kinds. They're either partial or they're ordinary. Now, I'm just going to talk about this a second, but the truth is, we don't do partial DEs. Not in this class. We don't do partial DEs. This is an introduction to ordinary differential equations. That's what this class is. There are more differential equations classes. There is advanced differential equations. There's partial differential equations. There's advanced partial differential equations. This is a very big, broad subject. You're getting one course, the introductory course of differential equations is what you're getting. What an ordinary differential equation is, and this is what we're studying, is that we have two variables. We have y, and y is a function of x, you know, and I just want to say that we refer to x as the independent variable. This is some language you might not have used too much in algebra or calculus, but x is the independent variable, and then y depends on that, so y is the dependent variable. And when we write our DEs, we can write them any way, but we typically, when we write dy dx, or we write y prime, I mean, then it's implied that y is the dependent variable, and y is a function of x, and we're taking the derivative of y with respect to the variable x. I mean, that's different than if I had dx dy, then I'd be talking about x as a function of y. Anyway, they've reversed roles if I'm talking dx dy. So usually this is the way we talk. Y is a function of x. Y is known as the dependent variable, independent variable. And those are ordinary differential equations. Our book does like to use all kinds of letters, though. You know, they use P's and Q's and R and S's. And so they're not in... The truth is, in real life, we often use y as a function of t, you know, time. And then there's times when we use x as a function of t. So now that gets a little confusing, but now t is the independent variable playing the role of x, and x is now the dependent variable sort of playing the role of y, right? But we use, you know, the independent variable tends to be time. It's often time, so we're often working with t's and time. What's partial? Partial is what we study in Calculus 3. Listen, we study functions of several variables. You know, and we won't do this in this class, and you didn't do this in Cal 1 or Cal 2 really. But when you get to Cal 3, you study functions of more than one variable. You're in 3 dimensions. You have an x, y, and z axis, and z is a function of 2 independent variables in a way, and z is the dependent variable. And when you take a derivative, you can take a partial derivative. You can take a partial derivative of z with respect to x, or you can take a partial derivative of z with respect to the variable y. And I can teach you how to do partial derivatives. It's real easy, I mean, but we won't need to. In this class, we're not going there. But I thought I'd tell you quickly what it was. More than one variable. More than one variable. All right, so we're studying ordinary DEs. All right, so then what? Oh, then you can classify these DEs, as to order. And order is just, it's easy. It's the number of the highest derivative in the problem. And so I kind of already told you it's the number of the highest derivative. So in chapter 1 and 2, we're really, well, not chapter. In chapter 2, like we just started, we're solving first order DEs. Everything you saw so far today has just had a y prime. It didn't have a second derivative, did it? You didn't see any y double primes or y triple primes. So everything we've done so far is a first order DE. If it has a y prime, it's a first order DE. If you see a y double prime, it's a second order DE. We'll learn how to solve those in chapter 4, some of those. When you're in chapter 1, they're trying to expose you to all this stuff. And so you might see some y double primes, some y triple primes. You're not solving them, but you're looking at them, and they'll say, what order is this? You'll say it's order 2, or order 3, or order 1. Or the order is just the highest, the number of the highest derivative in the DE. Then they classify these DEs as to being, these DEs can be linear or nonlinear. And we've probably seen a little of both today. That's a very subtle thing, this linear or nonlinear. But we need to have a discussion about it, I guess. This is all kind of in 1.1. This is, this is kind of how its course starts. I wanted you to see solving some DEs, so I started in 2.2. But this linear thing is a little funny. A DE is linear if it can be written in this form. Let me see what this says here. So it's linear if it can be written in this form. A n of x, d n y dxn. I mean, now we're talking kind of abstractly here. Can you tell me the order of this DE? Well, hang on a second. A n minus 1 of x, that's just a little subscript n and n minus 1. But it's multiplied by d n minus 1 of y with respect to x n minus 1. I mean, what is that? That's the nth derivative, right, you guys? So I wonder if you could tell me the order of this DE.
N.
Thank you, it's order n. Right, this could be a second derivative, this could be a third derivative, this could be a fourth derivative. Right, this is an nth order DE. An nth order linear DE is what this is. And it can be written in this form. Let me come on down here. A1 of x, y dx. So we're a subscript 0 of x times y equals f of x, or g of x. Wow. So what does it mean to be a linear DE? If it can be written in this form. Okay? If it can't be written in this form, maybe then it's nonlinear. So can you write it in this form? And now what do you see in this form? Let me show you what you see. You see a function y maybe, but maybe he's not there, You see a y prime, maybe you see a y double prime, a y triple prime, or what, right? That's
To the original function?
What'd you just say?
You're going down to the original function.
Yeah, thank you. You're going down, or I was starting here and going up, or however you want to say that. But yes, you got an original function y, or like the first DE I wrote today, or one of the first ones, not the first one, was this one. Is he linear or nonlinear? And by the way, what order is this one?
First order.
Thank you. It's first order. It's got a first derivative. Thank you. And is he linear or nonlinear?
Linear.
He is linear. He's not written in the form. To write him in the form, maybe you would move the 2y over, and it would look like this. And now look, is there a y term? Yes. What's the coefficient? This is the coefficient in front of the y term. And in this example, the coefficient is a 2. You know what this says is that the coefficient in front of the y term needs to be a function of x. That's what this says. It needs to. What that means is it better not have any damn y's in it. It better have x's in it. The coefficient in front of the y prime better have x's in it. And, well, not y's in it. It better be a function of x. Now you may look at this, this is just a 1, but is 1 a function of x? It's a constant. Yes, it is. It's not a function of y. So they're written in order. the coefficients should be functions of x. You know what else you see in this form is you don't see any y squareds or y prime squareds or anything like that. It might equal something over here on this side, and if it does equal something on this side, it better be a function of x. It better not be a cosine y over here. If it's a cosine y, that's not linear, I guess. See, this is a little bit difficult. To be linear, you fit this form. And if you don't fit this form, you're nonlinear. And to understand that, I'm trying to help you understand what this form is saying. There's sort of three ways, really there's sort of three ways to violate this form. Watch this. So this guy is linear. He is linear. Watch, how can I violate this form? I could do this. Watch, y double prime plus x y prime minus 3y equals cosine of y. Is this, first of all, what order is this?
Second.
Second order, thank you very much. You see y double prime is right there. Is he written in this form? Is he linear or not? And if he's not, why not? Which part of it does he violate? And I would say, so far, when you start over here, he looks like he might be linear. The y double prime has a coefficient of x, or a number, a coefficient of x or a number, a coefficient of x, a coefficient of a number or x. This is all good so far. No y double primes are being squared or cubed or square rooted. You can't have, they're all, I think that it's hard to say where this word linear comes from. We know what linear means back in algebra, right? It's a little weird up here in DE. But I'm going to speculate that none of the derivatives, listen, when you're solving a DE, who is sort of acting like the variable? Who are you solving for?
Y.
The function y, right. And so the function y and his derivatives are not squared or cubed or anything. The function y and his derivatives are not squared or cubed. I'm saying that's maybe where the word linear comes from. But there's nothing about this that's a line, okay? Nothing at all, really. Go ahead, Zachary.
Would it still be linear? Would it be linear if it was equivalent to cosine x?
Right. So I'm sitting here arguing that so far it's linear, but you're right. As soon as I come over here and see this, I have this function of, it's supposed to be a function of x. It's not, it's a function of y, so it's nonlinear. And you just asked me if it was a function of x, if this was cos x, would it be linear? And yes, it would be. Yeah. So this was the violation. Let's do another one. Watch this one. Y triple prime to the fourth plus 2y prime minus 6 square roots of y equals 0. Is this linear?
Yes.
No.
It's being raised.
And this one's nonlinear. Why is this one nonlinear?
The first term is raised to the fourth.
Yeah, you can't have that. None of these derivatives are all just derivatives. They're not a derivative raised to a fourth power. And this y is just a nice function of y to the first power. It's not a y squared or a square root of y. So the violation here is a couple places. That and that kind of make it nonlinear.
So it can't be a y to square root or exponent?
It's got to be just a nice y.
And this is, why is this?
The definition of being linear is, does it fit this form? And I'm trying my best to explain this form to you and what fits this form and what doesn't fit this form. And so far, I've explained two violations. What makes this not fit the form? What makes this not fit the form? And I got one more for you. Here's one. By the way, what order is this one? Second order, good job. It's a second order, ordinary DE, but it is nonlinear. This time it's nonlinear for the sort of the third violation. This one's nonlinear, and why is it? Do you see why?
Because of the negative 3y and y prime.
Yes, see, I look at these and I'm saying these things are coefficients of x in front of the y primes, or y double primes, or y primes, or whatever they are. In front of those are coefficients of x. Or a lot of times they're just numbers, which can be called a coefficient of x. But they're not y's. And I have that violation right here. Right. The coefficient in front of the y prime is a function of y. I got y's times y primes. That's nonlinear.
So basically, the dependent variable has to be a linear term, is what you're getting at?
Maybe that's what I'm saying. The dependent variable, which is y, and his derivatives, y prime, y double prime, have to be to the first power. Right? That was sort of this explanation. It can't be raised to the fourth or square rooted.
Or transcendental, so it can't be a trig function, or...
Yeah, I mean, that would kind of show up over here as like an e to the y or a cosine of y. I mean, that would sort of show up here, and that can't happen, right? We're not allowed to have that. We're not allowed to have this. We're not allowed to have that. And now I'm talking about the coefficient in front can't be a function of y, so we're not allowed to have this. Y times y prime, or y, right. So to tell you the truth, these are the three examples of what violates this form. I just found you three good examples of what violates this form and what makes it nonlinear. Yes, sir.
It would still be nonlinear if there was if, for example, 2y was missing, right?
Right. If the 2y was missing, it's still nonlinear, still based because of this, the coefficient, and right. All these terms don't have to be here. Like this one's got a y double prime, a y prime, and a y. This one's got a y triple prime, and then it skips y double prime. That's okay. So we can have missing terms, which means, I guess, these coefficients can be 0. It's okay for some of these coefficients to be 0 and have a missing term. That's okay. Yeah.
Could you call anything equaling a variable a linear different? Any x variable equaling 0. Could you call that a linear D? Any form of an x variable equaling 0?
You know, I'm losing track of that question. An x variable equaling 0.
Yeah, if it was raised to, like basically x to the n, but just that coefficient deal as well.
Does it mean it's linear because y depends strictly on x? And so if it's a function that when x changes, y is going to directly change, that's a linear function, right?
Yeah, I don't want to try to make a connection to the algebraic idea of linear. I really don't.
Yeah.
It's just a term. It's a term we use here in DE.
And then on this DE, this linear just means from the second derivative down to the first derivative down to the variable.
I mean, I really don't want to say it any other way than the way I've said it. To be a linear DE, you got to meet this form. So I don't.
That's simple.
And then, yeah, you got to be able. And if you can't get it into this form, then I guess it's nonlinear. And I've tried to explain to you sort of the three. There's only sort of 3 ways to violate this form, and I've sort of talked that through to you now. What are the 3 ways? This side needs to be a function of x. So if it's not, that's bad. The coefficients in front of all the y's need to be functions of x or numbers. And so if it's not, it's bad. It has to be a function of x. What was the other thing? Oh, all the derivatives and the y. Nobody can be cubed or squared or something or square rooted. That's nonlinear, right? Okay, so that's good. Listen, right there at the beginning of 1.1, they throw 8 or 10 DEs at you and they ask you, what's the order? Are they linear or not? And so you can practice that. It's not the hugest deal in the world, but it's worth discussing. It's worth trying to get your head around here. The other thing that happens in 1.1 is this. Watch this. Keep in mind that we're back to this preliminary theory in 1.1, and you don't know how to solve a DE. So they do this to you. Here's a differential equation. Y double prime minus 4y prime plus 4y equals 0. Y equals x e to the 2x is a solution. All right, so hang on. They gave me a DE. See that? That's a differential equation. By the way, it's second order, and I think it's linear. Who cares? All right, so there's a DE, and now they're telling me this is a solution. Well, thank you very much. And then but here's what they asked me to do. Please verify it. So they don't want me to verify it by solving it, because I don't know how to solve it, but this is good practice. This is the way a DE class always opens. They give you the answer to the DE, and they want you to verify it. And what that means is, if you plug it in, it'll work. But in order to plug it in, guess what you need?
Derivatives.
You need a derivative and a second derivative, and you can plug those in. If you take the first derivative and the second derivative and plug them in the appropriate spot, it should work. What does that mean? That means you'll get 0 equals 0. You'll get a true math statement. So now I'm going to try to do this. It's a bit pain in the ass because, all I got to do is a couple derivatives and plug them in. But why is this derivative a pain in the ass? Tell me.
Because
It's a product rule. But maybe we love product rules. Maybe we don't call them a pain in the ass. You ready? The derivative of the first. 1. Write down the second. Plus, write down the first. Take the derivative of the second. I'm doing a derivative.
2e to the
2e to the 2x. Awesome. That's my first derivative. I could clean that up a tad. Hang on. Well, I'm going to just leave it like that. Okay, I need a second derivative. You guys ready? Second derivative. Derivative of him. Just e to the 2x. The chain rule spits out a 2. 2e to the 2x. Derivative of him. Okay, well, it's a product rule. The first part is a 2x. So the derivative of the 2x is a 2. Write down the e guy. Plus, write down the 2x. And let's take the derivative of e to the 2x. The derivative of e to the 2x is 2e to the 2x. How you guys doing?
I would have just pulled the 2 out and treated the whole thing like 4x e to the 2x.
Sure. You mean right there at the end, that little
You just
loop?
multiply it all back in there.
Yeah.
Less adding.
And maybe when I go write it, I'm about to do that. I'm just doing it step by step. Both of these could be cleaned up a little. Well, not, yeah. You could factor, you could do some cool cleaning up, but really what I want to do is shove them in there and try to verify this. So here I go. I'm going to try to plug this in and see if it verifies. I hope it does. When I do plug it in, what I start with is y double prime, and as I plug that y double prime, I'm going to do what he said. I'm going to do a little cleaning as I put it in there. So this y double prime is a 4 e to the 2x plus a 4x e to the 2x. That's my y double prime, and it goes right there. Minus 4 times y prime. Okay, where's my y prime? Oh, there it is. So 4 times this would be an e to the 2x plus 2x e to the 2x. You guys okay? Plus a 4 times y, which is the original y. Where's the original y? Right there. X e to the 2x. Does this equal 0? I hope it does. They told me that they said it's a solution. Please verify it, so it should work.
I see terms cancel.
So I'm just rewriting this. I guess I'll distribute this. Negative 4 e to the 2x. Negative 8x e to the 2x. positive 4x e to the 2x. If you collect like terms, this x e to the 2x is one kind of term, and if you add those guys up, you get 0 of those. And these other guys are a different kind of term, and if you add those up, you get 0 of those. So you get 0 on the left-hand side equals 0 on the right-hand side. Is that true?
I hope so.
It's true, and we can verify it, and we can, so this is the work. It's kind of a little proof. It's like you knew the answer. They told you to verify it. There's kind of two kinds of questions. A lot of times they'll give you this solution. They'll say, dude, it is a solution. Please verify it, which means you know it's going to work. Just you got to do it to prove it. Sometimes they got a couple questions that they say, is it a solution or not? I mean, they leave you up in the air. They're not telling you it is. I guess you would try the same approach. You would try to prove that it is, and if you come out with a true statement, then yes, it is. If it comes out with a false statement, like 2 equals 0 or something like that, then it's not. Here, watch this. I'm kind of easing in. I'm going to quit here in about 5 or 6 minutes, but I'm kind of easing into 1.2, where I think you see a lot of similar kind of questions. Not too many new ideas, but there's this other kind of question. Look at this. They say this: y equals c1 cosine 2x plus c2 sine 2x. I'm making this up, is a solution of, it's a good question, I'm making up, of y double prime plus 4y equals 0. So, they're telling me there's a DE. They do this a lot because you don't know how to solve DEs yet in chapter 1. So they do this a lot where they talk about the DE. You're not supposed to know how to solve it. Oh, well, they're giving you the solution. They didn't really say verify it, but you could verify it. How would you verify it? Take a couple derivatives, plug them in, it should work, okay? But they didn't really say verify it. Instead, on this one, they're going to say this. Find, and they say it kind of funny. They say, find a particular member of the 2-parameter family of solutions. They refer to the C1 and C2 as parameters sometimes. I don't really do that. But reading this book is a little difficult sometimes. But they really are saying there's a 2-parameter family of solutions here. You've heard me use that word. And they're referring to the C1 and C2 as 2 parameters. They're saying find a particular solution, and then they need to give me a couple initial conditions. Watch. Find a particular solution if y of pi equals 3 and y of y prime of pi equals 4. I hope I can do this. It's possible I just set yourself up. It's possible I set this up where there is no answer. But what did I just do? I just gave you a couple initial conditions. What have you been trained to do with initial conditions? To find C. Right. What the hell do you do with initial conditions? You plug them in to help you find C. Right, exactly. And because there's 2 C's in this problem, we have 2 initial conditions. What I end up with here is 2 equations, 2 unknowns in a way, with looking for C1 and C2. One of these conditions is about the function y, so I can plug in that x and that y into the function y. This other condition is about y prime, which I think that means I need y prime, damn it. Let's get y prime. What is y prime? The derivative of cos. Negative sine of 2x.
2.
Chain rule spits out a 2. So negative 2c1 sine of 2x. Is that what we're saying?
Yes.
Plus the derivative of sine is cos. spits out a 2, so a positive 2c2 cosine 2x. So I can use these two initial conditions and try to find c1 and c2. Let's try it. In the original function, I'm plugging in a pi and I'm plugging in a 3 for y. Here we go. Plugging in a 3 for y, plugging in a pi right there, I get the cosine of 2 pi.
1.
That is a 1. I should have just wrote that instead of writing this out. And I get the sine of 2 pi. Look, I am writing this out when I plug in a pi, but I could save myself some steps. He's right. What is the cosine of 2 pi?
360 degrees, which is 1.
Which is a 1. What's the sine of 2 pi?
0.
A 0. Okay, so this is zeros out.
About your C2.
Well, it's just not there, right? This is 0 times C2, right? So this is a 0, that's gone. This is a 1, so guess what? C1 is 3. All right, maybe I don't have two equations, two unknowns. C1 is a 3. What does this say? If you plug pi into the derivative, you get 4. Okay, there's the derivative. Let's try it. If I plug a pi in, I get 4. If I plug a pi in, what is the sine of 2 pi?
0.
0. That term's gone. What's the cosine of 2 pi?
1.
A 1. That's a 2c2. Hey, cool. It doesn't take long to find c2. Divide by 2, and c2 is 2. Woohoo! We found it. And so we can write our answer. Our answer is a particular solution. It was, what was it? It was this general solution, but with these initial conditions, this general solution along with these initial conditions, we found the answer is, oh, there it is. C1 was a 3 cosine 2x, and C2 was a 2 sine 2x. Sweet. You guys okay? So in chapter 1, they're doing these little skill things, getting you ready for this course. They're doing some, this is stuff we need as we proceed through this course, to find the C's, to do some of this. But you're not really solving any DEs. I'm going to quit now, and it's time to go. I got another class at 10 o'clock. I can teach college algebra. I'm in my office at 12:30 for a little while.